We are on Chapter 5, Introduction to Solutions and Aqueous Reactions. The quote here is, "Science may be described as the art of systematic oversimplification, the art of discerning what we may, with advantage, omit." And that's especially true of Chem 1A, where we can take some of the inconvenient exceptions and pretend they don't exist. Solution concentration. So we've talked about what a solution is. It is a homogeneous mixture of two substances. And the concentration is going to tell us, how much of each part is in the solution. And this is important because many chemical reactions involve solutions where the reactants are dissolved in water. So there are two parts, the solvent and the solute. The solvent is technically the part that's present in greater amount. In an aqueous solution, water is always the solvent. The solute is what there's less of, the part that's dissolved in the solvent. You can have more than one solute, and how much solute there is variable, hence the need for concentration. So we can use qualitative descriptions such as dilute or concentrated, and this means the same thing here as it does in regular life. A dilute solution is going to have just a little bit of solute compared to the solvent, and a concentrated solution is going to have a lot more. So you can buy concentrated cleaning solutions, right? And those are advantageous because they're more cost effective to ship because they're not sending you all the water, right? And so you take it home and you pour some in your squirt bottle and you dilute it and you add water. And now you have a dilute solution. So that's the sort of thing we're talking about here. A common way, especially in chemistry, to express solution concentration quantitatively is molarity. Molarity, and the symbol is capital M. So this is the equation for molarity. The molarity is equal to the amount of solute measured in moles divided by the volume of the whole solution in liters. And this is a very, very important unit in chemistry. Here's an illustration of how you might make a solution of a specific concentration. Here we're trying to make a solution that is 1 mole per liter sodium chloride dissolved in water. So you would weigh out and add 1 mole of sodium chloride, which happens to be 58.44 grams, and then you would add that to a volumetric flask. This is a flask that's specifically designed to measure a particular volume. This is a 1 liter flask. Then you would add water. You want to do your mixing. Actually, you want to start mixing while you're adding the water, and then you'll fill it up so the bottom of the meniscus is right at the mark on the neck. Then you'll mix it some more and get all choked up just about the beauty of it. I don't know what that was. And then you end up with a 1 molar solution. So this being a 1 liter flask, 1 mole per 1 liter. Any questions? Okay, how many moles of solute would be needed to make 3 liters of a 2 molar solution? So this capital M is an abbreviation for moles per liter. So that's 2.0 moles per liter. So if we want 3 liters of the solution, how many moles do we need? 6. That's correct. This molarity, as you might have guessed with the per units, is frequently used as a conversion factor, and we can write it out like that here. Again, so the units cancel out. We're going to cancel out the liters, and we end up with 6 moles. Let's do another example. Calculate the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. So they're giving us some information. We've got 45.4 grams of sodium nitrate, and we have 2.50 liters. And they are asking us to find the molarity. So molarity, its equation is a little bit like the density equation, right? It's something divided by something else. And the only time we need to use those equations is when you're calculating the density or calculating the molarity. So here we are calculating the molarity. So the molarity is equal to the moles of solute, which in this case is the sodium nitrate, divided by the volume in liters of the solution. Well, they were kind to us here and they gave us the volume in liters, so we can just plug that one right in, 2.50 liters. But they gave us the mass of the solute, which is typical. Can we convert grams to moles? Sure we can. So what we want to do is take our 45.4 grams of sodium nitrate, and we want to convert this to moles. And we'll divide by grams to get those units to cancel out. And how do we find the number that goes in this conversion factor? Molar mass, so we need the periodic table, right? So sodium nitrate, there's one sodium, and there's one nitrogen, and there's 3 oxygens. And we add those up. Yeah, and my calculator was set up to do the tangent of a fraction. So I'm going to start that one over again because I don't want the tangent of this number. I really don't want the tangent of any number at this point in my life. Calculator says 85. Does that mean that this molar mass only has 2 significant figures? No. It means that the rest of the digits are 0, and our calculator, who doesn't understand significant figures, didn't write them. So we need to put the sig figs in there. This should have at least 2 decimal places. So 85 point, nope, that goes down here. 85.00 grams is 1 mole. Yeah, you might think that. It would make life easier for a lot of students if the scientific calculator could do sig figs. Unfortunately, it's really complicated, and significant figures are not universally used because they're actually a shortcut for something worse. Okay, 45.4 divided by 85. 0.5341 2 moles. 0.53412 moles, and I'm keeping those extra digits to avoid rounding errors. So I've got that number divided by 2.50, 0.213, and the next 2 digits. So that would be 0.214 capital M, which is the same as moles per liter. Any questions? Yeah. Yeah, the capital M stands for molarity. It stands for moles per liter. So the capital M is like an abbreviation for moles per liter. And, you know, I suppose if we dig, we could go back and find the history of that. My guess is that because molarity is by far the most common concentration unit used in chemistry, and it's like on all the, you know, you may have seen it on the reagent bottles, maybe you didn't realize what it was 16.0 capital M nitric acid, right? It's 16 molar nitric acid. And so it is shorter and easier than moles per liter. Unfortunately, it's also confusing to students. And even in Chem 1B, students forget that the capital M is mole per liter, and then that makes converting the units really tough. Yeah?
Is it okay to say molar instead of moles per liter? That's my professor last semester, not last semester, yeah. 3A said molar instead of moles.
Moles per liter or molar. So molar is like an adjective. So this would be a 0.214 molar solution. And I guess you could say the concentration is 0.214 molar.
Okay.
Yeah, I tend to use moles per liter because I really want to emphasize that that's what it means. Any other questions? Those are good questions. This kind of a calculation is as common as calculating and using molar mass to convert between grams and moles. So it's very, very common, and it's really important to understand moles per liter. So we can use molarity as a conversion factor. So if we have a volume of solution in liters, we can convert and find out how many moles of solute are in there. If we have the moles of solute, we can find out how many liters of solution we would need. Now, you can kind of anticipate that there's probably going to be some conversions that are tacked on to the beginning or the end. Because what if they give you the volume in milliliters? Well, then you have to convert it to liters, and then you go to moles. What if instead of the moles, you've got a mass, right? Well, then you mass to moles. But the molarity is the conversion factor between moles and liters for solutions. How many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? So we're going to approach these the same way we're approaching everything. We're going to highlight the numbers. We're going to highlight what we're trying to find, grams of sucrose. And then we will attempt to solve it using dimensional analysis, because that works most of the time. So I've been given two numbers. I've got 1.55 liters, and I have 0.758 capital M. The capital M is easier to type, but just like with density, with the slanted fraction, here we're writing with our hands, and so let's be clearer to ourselves what this is. This is 0.758 moles per liter. Because when you write it like that, now it looks like a conversion factor, right? So which of these units are we going to start with and convert into grams? We're going to start with the liters, right? This is going to be our conversion factor. This allows us to convert liters of solution into what? Moles, right? And then can we convert moles to grams? Yes, we can. Makes me think of Bob the Builder. Oh my goodness. Okay, so 1.55 liters times in a line, times in a line, liters to moles to grams. I'm going to put liter down here, so those cancel out. I'm going to put moles down here, so those cancel out. So here I have this relationship, right? It's this many moles per liter, per each liter, per 1 liter. So the number goes with moles. 0.758 moles per liter, if you want a number down there, per 1 liter. And then here I need the molar mass, so I'm going to have to calculate that. So 12 times 12.01 plus 22 times 1.008 plus 11 times 16 . 342.296. That's the mass of 1 mole of sucrose. So that's what I put in here for grams. And then I've got the math to do, 1.55 times 0.758 times 342.296 equals . My concentration and my volume both had 3 significant figures, so that's what my answer will end up with. So 402 grams of sugar. Yes?
You always have to use the molar mass, just whenever you're working with putting
Molarity?
Yeah, molarity.
You don't always need to use the molar mass. As we learned when we're dealing with chemical reactions, chemical equations, the chemical equation tells us how many moles of this reacts with how many moles of that. And so that's why chemists are so obsessed with moles, is because it's related to the particles interacting with each other. But then on the ends we have, well, what can we actually measure? So one of the nice things about concentration and molarity is that if you're going to do a stoichiometry problem, you don't need to use the molar mass then, because if you have the volume, you can go straight to moles. If you're doing a problem like this, where you're trying to figure out what's in the solution, then there's a good chance you'll need molar mass. Yeah. Anybody else? If we dissolve 25 grams of salt in 251 grams of water, what is the mass of the resulting solution? Well, let's think about it. You got 251 grams of water, and I'm going to put 25 grams of salt in it. Do I subtract those numbers? Or do I add them? Because when you mix two things together, their mass doesn't change, right? Law of conservation of mass. There's no chemical reaction going on here. Even if there was, the final mass would have to equal the sum of the initial masses, right? So it must be the 276. And that one just kind of comes at you from left field to make you think about it, right? Any questions about that? Solutions are often stored as concentrated solutions. We call them stock solutions. We keep them in the stock room. And then we make solutions of lower concentration for different experiments. And so what we do then is we're diluting the stock solution by adding more solvent. When we do this, the amount of solute doesn't change, just the volume of the solution. This is like buying a can of frozen concentrated orange juice at the grocery store. You come home and you put that into a 2-liter pitcher, right? And then you add some water. Well, did you get more orange goodness or less orange goodness by adding the water? No, you just spread it out, right? Because if you tried to eat it out of the can, it's like, well, maybe a little bit would taste good, but then it's just awfully sweet, right? And so we need to add some water to it. But all of the orange stuff that was in the can is in the solution now. The amount of orange stuff doesn't change, just the volume of the solution. So when we dilute a solution in chemistry, the moles of solute stay the same, We're just changing the volume. And so this brings us to an equation. M1 V1 equals M2 V2. This equation is pretty popular with students. And let's just think about what this is meaning. If I take the molarity of the first solution times the volume of this first solution, so the molarity would be moles per liter, and I multiply by the volume, that's going to give me the moles, right? So molarity times volume is the moles of solute in the first solution. When I dilute something, I don't change the number of moles. So the moles in the second solution have to be equal to the moles in the first solution. And the moles in the second solution are also described by the molarity times the volume, but for the second solution. What happens here is the molarity is going to be smaller and the volume is going to be bigger. Here's an example of diluting a solution. So here we're making 3 liters of 0.5 molar calcium chloride from a 10 molar stock solution. So we could say that this is volume 2, and this is molarity 2, and this is molarity 1. And we could calculate, using that equation, how much of solution 1 we need to use. So M1 V1 equals M2 V2. And I'm trying to solve for the volume that I need. So I'm going to divide both sides by the molarity of solution 1. And so I'm going to get 0.500 molar times 3 liters divided by 10 molar. It should be 0.150. So measuring out 0.150 liters of the 10 molar solution. We're going to pour it into a flask. And then we're going to add water to the mark, diluting it, changing the volume. But the number of moles in here are staying the same. And we could calculate that. The moles would be, what the, 0.500 moles per liter times 3 liters. It would be 1.50 moles in this amount of that amount of the initial solution. When I add water, I still have the 1.50 moles, but now I'm diluting it to a volume of 3 liters. So I take that number of moles, 1.50 moles, and I'm diluting it to 3 liters. No, what did I do? I was doing it backwards. This is the calculation for what needs to be in here. Not a good day for winging things. Yes? This is the amount of moles that we needed to get into the flask so that when we divide it, we get you know what? Can we just forget that part? That was unnecessarily confusing, I'm sorry. Awesome, any questions? To what volume in milliliters should you dilute 100 milliliters of a 5 molar calcium chloride solution? to obtain a 0.750 molar calcium chloride solution. Read the problem, highlight the numbers, highlight the question. So we've got 100 milliliters, and we have 5.00 moles per liter, and we have 0.750 moles per liter. Here's that magic word, dilute. We are diluting a solution. We can use the dilution equation. So the dilution equation says that the molarity of one solution times its volume equals the molarity of the second solution times its volume. So what we need to do is identify which one are we calling 1 and which one are we calling 2. It doesn't matter what you call them as long as you're consistent. So this is 100 milliliters of that concentration. Those are together, right? That's the volume of that particular concentration. Let's call those 1. Okay, that'll be solution 1. So then the 100 milliliters is the volume of solution 1, and the molarity of solution 1 is 5. And then these guys are going to belong to solution 2. This is the thing that students seem to have the most trouble with, is getting the labels assigned correctly. So this is describing solution 2. We don't know what the volume is. That's what we're trying to find out, but we do know the concentration. So the molarity for solution 2 is right there. So we're trying to find volume 2. So that's this guy. There's a little bit of algebra involved here. So what I want to do is I want to move the M2 over to this side, so I get an equation that says V2 equals something. It is almost always better to rearrange the equation when you just have nice short little variables instead of when you get all these messy numbers and units in there. So I'm going to divide this side by M2, and I'm going to divide that side by M2. I do the same thing to both sides, and so they are still equal. Volume 2 equals M1 V1 over M2. So the molarity of solution 1 is 5.00 moles per liter. The volume of solution 1 is 100.0 milliliters. And the molarity of solution 2 is 0.750 moles per liter. Do the units cancel out? Yeah, they do. I have moles per liter up here, and I have moles per liter down there. So those guys are going to cancel each other out. And my answer is going to be in milliliters. One of these days I'm going to go in and change these numbers because 666. 3 steak figs, right? So 667 milliliters is what you need. So we're taking 100 milliliters of this more concentrated solution, and we're making it less concentrated. That makes the volume bigger. If you get your 1s and 2s backwards, then you're going to end up with you're diluting it and you're making the volume smaller, and that's just not how it works. Any questions? If you feel more comfortable converting milliliters to liters, and then doing the equation and then converting liters back to milliliters, that's absolutely fine.